You know, when you see a large language model work its magic, it can feel, well, almost supernatural, right? One second, it's writing a beautiful poem. The next, it's finding a bug in your code. So let's pull back the curtain, because under all that magic, there are two key things that make it all happen. And that's the thing. Their power is just so incredibly broad. They can translate languages on the fly, they can summarize super dense documents, they can even help scientists solve complex problems. You almost feel like you're talking to a real intelligence. But how? How does it really work? Well, the secret isn't just one single breakthrough. It's actually this incredible combination. First, you've got the brain. That's the computational engine, a totally groundbreaking architecture that changed everything. And then you have the food, the absolutely massive, high-quality diet of data it needs to learn. So let's start with the brain.
Okay, so the brain inside pretty much every modern LLM is an architecture called the transformer. And you got to understand, this wasn't just some small upgrade. This was a total paradigm shift for the entire field of AI.
This right here, this was the Big Bang moment. A paper from 2017 with this incredibly bold title just completely flipped the script. See, before this, models like RNNs had to read everything word by word in a straight line. It was slow, and they'd often forget the beginning of a long sentence by the time they got to the end. The transformer introduced a whole new way of thinking, all built around a single idea: attention. And that core idea is called the self-attention mechanism. And it's brilliant. It lets the model look at an entire sentence all at once. And for every single word, it figures out how important every other word is to it. So in a sentence like, "The cat that sat on the mat was purring," self-attention can immediately link cat to purring, no matter how many words are in between. This means it can process things in parallel way faster, and it gets a much, much deeper sense of context. So how does it actually do that? Well, think of it like a really sophisticated file lookup system. For every word, the model creates three little vectors. A query, which is like asking, what context am I looking for? A key, which says, here's the kind of information I have. And a value, which is the actual information itself. The model then matches the query with all the most relevant keys in the sentence and uses their values to build this incredibly rich, context-aware picture of what's going on.
Of course, attention isn't doing all this heavy lifting by itself. You've got these other critical parts that are like the brain's support systems. Positional embeddings, for example, are what give the model a sense of grammar and word order. Activation functions let it learn really complex, non-obvious patterns. And then things like residual connections and layer normalization, they're like the essential safety checks that keep the whole training process stable, which is what lets us build these networks to be so unbelievably deep and powerful.
Now, not all these transformer brains are identical. They come in a couple of different flavors, specialized for different jobs. You've got encoder-decoder models, like Google's T5. These are fantastic for tasks like translation, where they first read the entire input sentence to get the full context, and then they start generating the output. On the other hand, you have decoder-only models, like the GPT family. These are masters of generation, building things out one word at a time, which makes them absolutely perfect for things like chatbots and code completion. So we have this incredible brain. It's powerful, it's fast, it's complex, but even the most brilliant brain in the world is useless if it doesn't know anything. And that is where the food comes in. The data an LLM eats is every bit as important as the architecture that's doing the thinking. And this right here is the absolute, unbreakable, golden rule of all machine learning. The model's accuracy, its reliability, even its potential biases, it's all a direct reflection of the data it was fed. You see, high-quality data is the lifeblood. It's what makes the difference between a model that's helpful and trustworthy and one that's just confidently wrong. And the scale of this diet is just, it's hard to even wrap your head around. To put it in perspective, Meta's Llama 3.1 model was trained on 15.6 trillion tokens. That's not a typo. Trillion. There is no way you can manually clean or curate a data set that huge. It's just not possible. And that's why the process for preparing this data has become this incredible feat of engineering all on its own. So how on earth do you prepare a meal that big? Well, it's not like just downloading the internet. It's this whole sophisticated pipeline. First, you have these basic filters that just get rid of the obvious junk. Then you run it through advanced deduplication to make sure the data is varied. But here's the crazy part. They then use other machine learning models to score all that text and pick out only the highest quality stuff. And finally, a decontamination step to make sure the final exams are fair.
And even just that one step, deduplication, has gotten so much more sophisticated. In the old days, you'd just find and remove exact copies of text. Then we got better at finding near duplicates. But today, the state-of-the-art methods use something called embeddings to find content that's semantically similar, meaning text that says the same thing even if it uses completely different words. This forces the model to learn concepts, not just memorize phrases. And this is where it gets really meta. We're now in an era of ML for ML. We are literally using AI to prepare the food for a bigger AI. These smaller, highly specialized models act like data connoisseurs, sifting through mountains and mountains of information to find the most nutritious, highest quality text for the big LLMs to learn from. So why go through all this trouble? Well, that last step, task decontamination, is absolutely vital for scientific rigor. You have to remove any questions from the model's final exams, its benchmarks, from its training data. It's the only way to make sure you're testing what the model has actually learned to figure out, not just what it memorized from its study materials. It's about testing for genuine intelligence, not just a good memory. Okay, so let's bring it all back together. We have the brain, the architecture, and we have the food, the data. This is where the real magic actually happens, because as you've seen, it's not one or the other. You can't have one without the other. You can have the most brilliant architecture in the world, but if you feed it garbage data, you'll get garbage results. And the most pristine, perfect data on the planet is useless without a brain powerful enough to actually learn from it. So on one side, you have this revolutionary transformer brain with its self-attention mechanism that can understand relationships and context at a scale we never thought possible. And on the other, you have this meticulously prepared, high-quality food it needs to consume. That data pipeline is really the unsung hero in all of this. It's providing the refined fuel that makes all that amazing performance possible. And that leaves us with a really important and kind of tricky question for the future. As AI starts to generate more and more of the content on the internet, what happens when the next generation of models starts training on that data, on the creations of their own predecessors? Making sure the AI's diet stays high quality might just be the biggest challenge we have yet. Something to think about.